Welcome students. In this lecture we will be seeing volumetric stress and strain, volumetric strain of a rectangular bar and volumetric strain of a bar of circular cross section. Then we will be deriving the volumetric strain equation using generalized Hooke's law. Then we will be deriving the relationship between the three elastic constants. First, volumetric stress and strain. Consider an element or cube like this. This cube is subjected to equal stresses in three mutually perpendicular directions. So let the stress value be sigma. When such a body is immersed in any fluid or liquid, what happens is a pressure will be acting on the element. So I can say sigma is equal to minus P. So this P is the pressure which is compressive in nature. So if the body is subjected to such stresses, there will be a change in volume, but no change of shape will be there. The volumetric strain for this case is given by the change in volume by the original volume. We know that bulk modulus is equal to stress by volumetric strain. In this case, the stress sigma is equal to minus P and volumetric strain is given by del B by V. Here K is the bulk modulus and P is the pressure, del V by V is the volumetric strain. Or I can say volumetric strain is equal to minus P by K. Here a negative sign is used because with an increase in pressure the volume decreases. So both will be having an opposite effect. That's why negative sign is used. And the unit of bulk modulus is Newton per meter square, because K is equal to minus P by del V by V is the equation. Here del V by V will be having no unit and P will be having the unit of Newton per meter square. So I can say bulk modulus We'll also have the units of pressure, that is Newton per meter square. Now we shall find the volumetric strain of a rectangular bar. Consider a body as shown in the figure. The dimensions are L, B and D. So this is length and this is B and this is D. So the volume is given by the product of L, B and D. The change in volume is given by, see, this is of the form UVW. If you have to integrate this UVW, you have to differentiate one term and keep the other two terms as constant. Similarly, I have to do for this. I am keeping L, B constant and differentiating D. Next, I am keeping L and D constant and differentiating B. Next, I am keeping B and D constant and differentiating L. So the volumetric strain is given by the change in volume by the original volume. So this becomes LB delta D plus LD delta B plus BD delta L divided by L B D. So volumetric strain is equal to, here LB gets cancelled and here the LD gets cancelled and here BD gets cancelled. So finally I'll be having like this, delta D by D plus delta B by B plus delta L by L. So this is the volumetric strain. When you notice this equation, we can say that this three terms are the strains in three directions. If I consider the direction as X, Y and Z, then delta D by D is epsilon Y. Delta B by B is the strain in Z direction, so I can write it as epsilon Z, and delta L by L is the strain in X direction, so I can write it as epsilon X. So the volumetric strain is given by the sum of strain in X direction, strain in Z direction and strain in Y direction. So this is the equation. Similarly, we can find the volumetric strain in a bar of circular cross section. The volume is given by pi by 4 d square L the change in volume is given by pi by 4. I can keep it as a constant. I am differentiating L. So if you differentiate L, I will be getting del L. Now I am keeping L as constant and differentiating d square. D square and differentiating will give 2d into del D. So the volumetric strain is given by delta V by V. This is equal to pi by 4 d square delta L plus L 2d into delta D divided by pi by 4 d square. So if you cancel the pi by 4 and solve this, you will be getting, and the denominator will be having pi by 4 d square L. So this on cancellation gives delta L by L plus 2 delta D by D. So I can write volumetric strain is given by delta L by L plus 2 into delta D by D. Generalized Hooke's law. Consider an element like this as shown in figure, subjected to normal stresses sigma x, sigma y and sigma z. So this is sigma x. So in this, the strain in x direction is given by sigma x by E. So the strain in x direction is given by sigma x by E minus Poisson's ratio into sigma y by E minus Poisson's ratio sigma z by E. Similarly, for y direction, the strain in y direction is given by sigma y by E minus mu sigma x by E minus mu sigma z by E. If the length is increasing in one direction, the dimensions in the other two directions decreases. That's why the minus term is indicated. So this two terms accounts for the lateral strain and this for the longitudinal strain. Similarly, for strain in the z direction, I can write sigma z by E minus Poisson's ratio sigma x by E minus Poisson's ratio sigma y by E. So if I calculate all the three equations, I will be getting the total strain. So the total strain is given by epsilon x plus epsilon y plus epsilon z. So when you add all this, I will be getting sigma x by E plus sigma y by E plus sigma z by E. First I am adding these three terms. Then I am adding sigma x terms in the remaining part. So here I am having one sigma and here I am having one sigma. So when you add this, I will be getting 2 mu sigma x by E, then 2 mu 2 sigma y by E minus 2 mu sigma z by E. So this, if you solve, it will give sigma x plus sigma y plus sigma z by E into 1 minus 2 mu. So this is your final equation. For a state of uniaxial stress along x-axis, for a state of uniaxial stress, for a state of uniaxial stress along x-axis, sigma y is equal to 0 and sigma z is equal to 0. And for a state of biaxial stress along x and y axis, sigma z alone will be 0.